Okay, let's unpack this. Think about the very heart of everything around us, the atomic nucleus. For years, we've understood the dance between that nucleus and its electrons, the electromagnetic force that governs so much of our technology.
Right. That's the picture most people have.
But what about inside that nucleus? What actually makes up the protons and neutrons? That's where our picture gets a bit, well, fuzzier.
Uh-huh. We know they're there, but the inner workings.
Exactly. The force holding them together, the strongest force in nature that's still largely a realm of mystery. But get this. Scientists are building an incredible new machine to peer into that fundamental level, even beyond protons and neutrons.
It's really quite mind-boggling when you think about the scale of this. We've spent decades probing atoms, their components. Now we're aiming to, dissect the very building blocks of those components.
Yeah,
This isn't just a minor tweak to existing tools, it's a fundamental leap in how we explore the nature of matter itself.
absolutely. And this leap is called the Electron-Ion Collider, or the EIC. Now, this isn't some small lab experiment we're talking about. Imagine a cutting-edge particle accelerator on a massive scale,
Huge scale.
currently under construction at Brookhaven National Laboratory right here in the U.S. In fact, it's the only large-scale accelerator facility planned in the States for the coming decades, and it's genuinely one of the most sophisticated scientific instruments being built anywhere.
And if you connect this to the bigger picture of high-energy physics research, the EIC fills a really crucial gap. We've had fixed target experiments.
Right, firing beams at stationary things.
Exactly. And then we have the high-energy colliders like the LHC smashing particles together at incredible speeds. The EIC operates in an intermediate energy range, but with a unique and powerful capability. It can highly polarize both the electron and proton, or ion, beams.
Polarize, meaning getting their spins lined up.
Precisely. Achieving an alignment of their intrinsic spin of around 70%. This level of control is something we just haven't had before in this kind of collider.
So if you've ever wondered, what are the fundamental components of a proton? What's the super strong glue holding it together? Or even how fundamental properties like mass and spin actually arise at that level? Well, then you've come to the right place.
Definitely.
And don't worry if particle physics sounds intimidating. We're all about unpacking these complex ideas in a clear way, focusing on the why it matters and those potential aha moments.
Making it accessible.
Our mission for this deep dive is pretty straightforward. To understand the core purpose of the EIC. What secrets of this strong nuclear force is it specifically designed to unlock by colliding these highly controlled beams of polarized electrons with polarized protons and light ions?
And that raises a really important point. What are the specific scientific puzzles the EIC is designed to tackle? The sources highlight some truly fundamental questions.
Like what?
Well, first, how do the properties we observe in nucleons, things like their mass and their intrinsic angular momentum, their spin, how do those actually emerge from the partons, the quarks and gluons inside, and the way they interact?
Okay, so where does mass itself come from at that level?
Right. And the second key question is, how are these partons distributed inside the nucleon? Not just their energy and momentum, but also their distribution in space. It's like trying to create a detailed 3D map of all the ingredients inside something incredibly tiny and constantly moving.
A super energetic and incredibly small object.
Yeah.
And there's even more that EIC aims to explore, isn't there?
Oh, absolutely. The EIC will also investigate how these quarks and gluons, which carry this color charge, kind of analogous to electric charge, but for the strong force,
Right.
and the showers of particles called jets that they produce, how do they interact when they're inside a nucleus, a nuclear medium? How do these fundamental bits eventually come together to form the confined hadronic states, the protons and neutrons themselves?
Hmm.
And maybe most fundamentally, how do these interactions between quarks and gluons actually create the force that binds the nuclei of atoms together?
Wow. So it's not just about taking a snapshot. It's about understanding the very essence of what holds matter together at its core. And beyond these central questions, the EIC has a really broad program of fundamental QCD measurements planned. Now, QCD is quantum chromodynamics.
The theory of the strong force.
Right. This isn't some isolated experiment. The data it collects will have significant implications for a wide range of current and future research in high-energy physics.
And what's really exciting to consider is the potential reach of this research. The EIC's insights into QCD won't just deepen our understanding of the strong force itself, but they could also have these knock-on effects, providing crucial information for our ongoing search for physics beyond our current best theory, the Standard Model.
Okay, so we have a sense of why this amazing machine is being built. But what is it exactly? You mentioned it's a collider. Can you sort of paint us a bit of a picture? What should we be imagining?
Okay, picture two very long opposing tubes like racetracks for particles, almost circular. In one tube, you have a beam of electrons, and in the other, a beam of protons, or maybe heavier atomic nuclei, which we call ions. The EIC will use powerful magnets to accelerate these beams to incredibly high speeds, really close to the speed of light.
Right.
Then, at specific points along these rings, the two beams will be steered to collide head-on with tremendous energy. And as we mentioned, a really key feature is the ability to control the intrinsic spin of these particles.
The polarization again?
Yes, ensuring that a large fraction of both the electron and the ion beams have their spins aligned in a particular direction. This high polarization allows scientists to probe the details of their interactions much more precisely.
And the energy. You said intermediate.
Yeah, the EIC operates in that intermediate energy range. It offers a kind of sweet spot between getting a more static, detailed look like in fixed target experiments and the ultra-high energy collisions of places like the Large Hadron Collider, which can sometimes be, well, harder to interpret due to their complexity.
Right, so it's about creating these really controlled, high-precision collisions that let us carefully examine what happens in the aftermath.
Okay, so
Right.
the EIC is going to be this incredibly powerful microscope for studying the strong force. Let's dive into some of the specific areas where it's expected to make major breakthroughs. Maybe starting with the exciting possibility of seeing physics beyond what we currently know, beyond the Standard Model.
Yeah, this is a really exciting aspect. What makes the EIC truly groundbreaking here is that its unique capabilities open up entirely new ways to look for physics we haven't encountered yet, compared to AUNI, the only previous electron-proton collider.
Right, in Germany.
The EIC will have vastly higher luminosity. Now, luminosity in particle physics is basically a measure of how many collisions happen per second.
So higher luminosity means more collisions.
Way more collisions. A higher luminosity means we get much, much more data in the same amount of time.
More crashes mean more chances to see something totally new and unexpected, right? Precisely. It's not just about collecting more of the same data. It pushes us into regimes where extremely rare events might actually become statistically significant. We might see fleeting glimpses of new particles or interactions that were just invisible before.
Oh.
And then you have that crucial aspect of polarization we keep coming back to. The EIC will be the first collider of leptons, like electrons and ions, where both beams can be highly polarized.
Both. That's new.
Yeah. And what's more, scientists can actually flip the electron beam's helicity, its spin direction relative to its motion right at the source. This unprecedented control allows for very precise measurements, including the direct extraction of what are called parity-violating components in electroweak neutral current scattering.
Okay. Parity violating.
Mm-hmm.
That sounds really interesting, like looking in a mirror and things being different. What does that tell us about potential new physics?
Exactly like that. Parity violation refers to a specific kind of asymmetry in fundamental interactions, where a process doesn't behave the same way as its mirror image. The ability to directly measure these parity-violating components and to perform the very first measurements of polarized neutral current structure functions gives us a really sensitive probe for new fundamental forces or particles that might interact differently with particles that have a left-handed spin versus those with a right-handed spin.
So it's like having a brand new way to sort of feel for subtle imbalances or differences in the universe that the Standard Model, our current best understanding,
Right?
might not be able to explain.
That's a great way to put it. Think of it like having a new sense to detect subtle flavors in a dish that you couldn't taste before.
Okay.
Furthermore, the EIC's high luminosity significantly increases our sensitivity to other kinds of rare processes. We might get a much better look at charged current electroweak interactions, and perhaps even catch a glimpse of something called charged lepton flavor violation.
Whoa, what's that?
That's where one type of lepton, say an electron, might transform into another, like a muon or a tau. This is something the standard model strictly forbids.
Strictly forbids, so finding it would be huge.
Absolutely monumental. Any evidence of it would be a major discovery. There's also the exciting potential to discover hypothetical heavy photons particles like the photons we know, but with mass, or even find evidence of Lorentz and CPT violating effects.
Which would challenge fundamental ideas about space and time.
Exactly. They would challenge some of our most fundamental assumptions about the nature of space, time, and the properties of particles.
Wow. So the EIC isn't just about looking deeper into what we already know. It's also about potentially opening up entirely new chapters in physics. And how does it fit in with other big facilities like the LHC at CERN? Are they competitors or collaborators?
That's a really crucial point. They're designed to be complementary tools. The LHC primarily collides protons with protons, reaching incredible energies. But these collisions are, well, messy, very complex events.
There's lots going on.
The EIC, with its cleaner collisions between electrons and protons or nuclei at somewhat lower but still significant energies, provides a different, more controlled perspective. It's particularly valuable for probing indirect signs of new physics within a framework called the Standard Model Effective Field Theory, or SFFT.
SMMFT.
Okay. This lets us look for very subtle deviations from the standard model's predictions in a, let's say, more well-understood experimental environment.
So the LHC might find a little bump in its data that hints at something new, and then the EIC can help us zoom in and understand exactly what's causing that bump with much greater precision.
That's a great analogy. The EIC can also give us much more detailed information about the quarks and gluons inside the proton. Its enhanced sensitivity to different flavors of quarks, including the strange quark, through those parity-violating asymmetries we talked about, is particularly important.
Ah, the strange quark.
Yeah, our sources mention how EIC data could significantly improve our understanding of quantities related to the spin contributions of different quarks and gluons within the proton.
And the strange quark has always been a bit of a puzzle in the proton's structure, hasn't it? So the EIC could really help fill in some missing pieces there. The sources also briefly mentioned leptoquarks. Those sound like something straight out of science fiction.
They do have a fantastic name. Leptoquarks are hypothetical particles that would essentially bridge the gap between leptons, like electrons, and quarks. They'd mediate interactions between these two, usually separate families.
Connecting electrons and quarks directly. Interesting.
Yeah. The EIC's potential to set limits on the existence and properties of scalar leptoquarks is really interesting. The sources even compared the expected sensitivity at the EIC to HEA and other experiments like Baybar. While EIC did look for these, the EIC's higher luminosity and its other advanced features give it a real advantage. It could either discover them, or if they don't exist at the energies the EIC can probe, set much stricter constraints on their possible properties, like their mass.
Okay, so beyond the exciting hunt for brand new particles and forces, the EIC is also designed to give us a much, much clearer picture of what's actually inside the protons and neutrons we already know about. Let's talk about this tomography of hadrons and nuclei. It sounds like we're going to get a detailed 3D map of the subatomic world.
That's precisely the goal. For the first time, the EIC will create comprehensive maps of the internal landscape of hadrons, especially the proton, and also of light and heavy atomic nuclei. This tomography we're talking about refers to getting detailed information about the non-perturbative distributions inside.
Non-perturbative. That sounds like the really complex, hard-to-calculate aspects of the strong force, right? Where that math gets tricky.
You've got it. These distributions describe the fundamental structure, Parton distribution functions, PDFs, transverse momentum dependent, TMD distributions, and generalized Parton distributions, GPDs. But they're governed by the strong force at energy scales, where our usual perturbative methods.
The tools for weaker forces like electromagnetism?
Right, those tools don't work so well. The strong force is just too strong at those scales. That's why these distributions are so challenging to study theoretically and often represent the biggest sources of uncertainty in our predictions for high-energy physics experiments. The EIC is really designed to specialize in pinning down these very fundamental objects that currently limit the precision of our understanding across various fields, from collider experiments to neutrino physics.
So by getting a much better handle on these fundamental building blocks within protons and neutrons, the EIC will actually improve the accuracy of experiments happening at other facilities around the world.
Yeah.
That's a really fascinating knock-on effect.
Absolutely. It feeds back into the whole field.
The sources mention something called the Wigner function.
Yeah.
That sounds like it's at the very heart of this detailed tomographic view.
The Wigner function gives us the most complete, although also maybe the most mathematically complex, picture of the protonic structure. It essentially tries to describe the distribution of partons, quarks, and gluons, not just by their momentum, but also by their position in space simultaneously.
Position and momentum. That's usually forbidden by quantum mechanics, isn't it?
Well, it's a quasi-probability distribution, so it's not quite a classical picture, but it encodes that information. While it's quite abstract, the crucial thing is that we can, in theory, derive other, more familiar distributions from it. For example, by mathematically integrating over the transverse momentum, we get the collinear PDFs.
Which tell us how much momentum each parton carries.
Exactly, the fraction of the nucleon's total longitudinal momentum carried by each type of parton.
And then TMDs and GPDs come from other specific ways of mathematically kind of slicing or integrating this Wigner function, giving us different kinds of information about the 3D structure and dynamics.
Precisely. TMDs give us information about the transverse momentum, that sideways motion of the partons within the nucleon. GPDs encode information about their spatial distribution, essentially allowing us to create those tomographic 3D images you mentioned.
Got it.
It's really important to remember that these distributions are fundamentally non-perturbative. At the energy scales corresponding to the size and mass of protons and neutrons, the strong force is just too strong for our standard perturbative calculation techniques to be fully reliable.
So we need experiments.
We absolutely need experiments. Methods like lattice QCD, using supercomputers to simulate the strong force, provide valuable theoretical insights, but ultimately, high-precision experimental data is absolutely crucial for fully understanding these distributions.
And that's precisely where the EIC comes in. The sources also talk about something called QCD global analysis. What's that all about, and how does it relate?
QCD global analysis is the main technique physicists use to extract information about hadron structure from the huge amounts of experimental data collected over decades. It involves taking our best theoretical calculations, which incorporate these non-perturbative things like PDFs and are based on QCD factorization principles, and then fitting these calculations to a wide range of experimental measurements from different kinds of processes, deep inelastic scattering, Drell-Yan, jet production, etc.
Combining everything.
Exactly. By combining data from many different experiments, we build up a more complete and precise picture of the partonic structure. The high-precision data the EIC will produce will be an absolutely crucial input for future QCD global analyses, significantly improving the accuracy of our knowledge of these fundamental distributions.
Okay, so the EIC isn't just about making new discoveries. It's also about bringing a whole new level of precision to our understanding of QCD, the strong force theory. Let's delve a little deeper into that precision aspect, specifically in perturbative QCD, where calculations are more reliable, and the electroweak sector.
Right. The EIC, by performing a wide variety of measurements up to a center of mass energy of about 140 GeV in the relatively clean environment of electron-proton and electron nucleus deep inelastic scattering, DIS,
Okay.
it will allow us to probe fundamental aspects of QCD that are really difficult to isolate in the much messier hadron collisions at, say, the LHC. This includes detailed studies of heavy quark production charm and bottom, and also the production of jets in these DIS processes.
Cleaner collisions make for cleaner measurement.
Exactly. These kinds of measurements provide information that complements the inclusive structure function measurements we talked about earlier, and they'll be vital for future QCD global analyses. By bringing together these different types of high-precision data, we can achieve much more accurate separation of the different quark flavors, both polarized and unpolarized, within the proton and neutron.
Separating up quarks from down quarks, strained quarks.
Yes, and understanding their spin contributions, too. We can also significantly improve our determinations of fundamental QCD parameters, like the strong coupling constant, alphas, and the precise masses of the heavy quarks.
So these cleaner electron-based collisions lead to more precise measurements of the fundamental constants of nature related to the strong force. That sounds incredibly important. And how does this improved precision at the EIC then impact our understanding of other phenomena at different colliders?
The improvements we expect in our knowledge of parton distribution functions, the PDFs, from EIC data will have a really significant impact across high-energy physics. The sources specifically mention the production rate, the cross-section of the Higgs boson at the LHC.
Higgs connection.
Right. The main way Higgs bosons are produced at the LHC is through the fusion of two gluons.
Hmm.
So the precision of our knowledge of the gluon PDF inside the proton is absolutely crucial for predicting how many Higgs bosons we should see.
Makes sense.
Projections based on simulated EIC data show that the EIC has the potential to significantly reduce the uncertainties in our knowledge of the gluon PDF. This, in turn, would lead to much more precise predictions for Higgs production at the LHC. The EIC probes specific ranges of momentum fraction X and energy scale that are particularly sensitive for Higgs production.
That's a fantastic example of how the EIC can directly contribute to understanding even the most recently discovered particles. The sources also touched on forward physics at the LHC. What's the connection there, and why is the EIC relevant?
Forward physics looks at particles produced at very small angles to the colliding beams. It's becoming increasingly important at the LHC and for future hadron colliders. It's relevant for studying various QCD phenomena like diffractive processes and even for certain BSM searches.
Okay.
However, at the lower transverse momentum typical of forward physics, theoretical uncertainties related to hadronization, how partons turn into hadrons plus higher order corrections, and the underlying event become quite significant.
So the theory gets complicated in that region.
It does. The cleaner experimental environment of the EIC, using a well-understood electromagnetic probe where QCD factorization holds more reliably, will be incredibly valuable for testing the theoretical calculations and models used to interpret forward physics data from hadron colliders.
So the EIC can act as a sort of testing ground or calibration tool for the models we use to understand these extreme forward collisions at the LHC.
Exactly. We can use EIC data to rigorously test the Monte Carlo event generators, these sophisticated simulations modeling the whole collision process, including parton fragmentation, parton showers, and matching calculations to showers. We can do this in a much more controlled setting at the EIC. Studies of low transverse momentum jets produced centrally may be associated with forward activity like another jet or an intact proton will be particularly useful. Even looking at particle production probability changes when there are gaps can help refine our understanding of color flow in simulations. The excellent tracking at the EIC detectors will also allow a study of very low transverse momentum jets and hadrons, providing stringent tests of models directly applicable to hadron collider data interpretation.
It sounds like the EIC and the LHC are going to have a really symbiotic relationship, each helping refine our understanding of the other's data. The discussion then moved on to jet substructure, another area where the LHC has made big strides. How will the EIC contribute here?
Jet substructure analyzing the internal pattern of particles within a jet has indeed become a powerful tool at the LHC, especially for finding new heavy particles decaying into jets. The EIC will let us do similar investigations on jets with lower transverse momentum.
Lower energy jets.
Right. While these jets might have fewer particles than high-energy LHC jets, they can still offer valuable insights into fundamental jet properties relevant elsewhere, like the low PT jets that pop up in electroweak analyses.
So it's about expanding our understanding of jet structure to a different energy regime.
Precisely. Finally, the sources highlighted the increasing importance of including very precise QED corrections from quantum electrodynamics in high-precision hadron collider measurements.
QED, the theory of light and electrons.
Yes. Because photons can be emitted from the initial protons, we need to consider the photon content of the proton, similar to quarks and gluons, leading to a photon parton density.
A photon PDF. Interesting.
Yeah. The EIC will contribute to understanding these photon PDFs and also isospin violating effects, which matter at high precision. Frameworks like LUX-QED relate the photon PDF to measured proton structure functions, and EIC's high-precision measurements will help refine these models and the combined QCD plus QED evolution equations.
And this helps LHC predictions.
Absolutely. This improved understanding of the proton's photon content directly impacts the accuracy of predictions for electroweak processes like W&D boson production at the LHC and future colliders.
It's just amazing how interconnected all these different aspects are and how the EIC is poised to make really significant contributions across so many research fronts. Let's now focus more specifically on the collinear structure of hadrons and nuclei, starting with the unpolarized parton distribution functions, PDFs. We've touched on PDFs, but can you elaborate on how the EIC will significantly improve our knowledge here?
Okay. The EIC has a dedicated, comprehensive program aimed at precisely determining the unpolarized quark and gluon PDFs of the proton down to very small x values, around 10 mMol.
Really small momentum fractions.
Exactly. This is crucial because these low X gluons play a significant role in standard candle measurements at the highest energy colliders, like Higgs production at the LHC, as we mentioned. By performing a wide array of deep inelastic scattering measurements, the EIC will directly address several limitations in our current understanding. This includes much greater sensitivity to parton behavior at high X.
Close to the proton's full momentum.
Right, allowing us to investigate subtle effects like higher twist contributions and target mass corrections. And importantly, this high X region is particularly relevant for constraining potential BSM signatures in Drell-Yan processes at the LHC, which often involve interactions at very large energy scales.
So the EIC will give us a much better handle on the proton's quark and gluon content across a much wider range of momentum fractions, from tiny fractions up to almost the whole thing.
Exactly. And at the very small X end, the EIC has unique capabilities for investigating phenomena like gluon saturation.
Where gluons get so dense they recombine?
Potentially, yes. And other effects described by low X resonation techniques. These phenomena might cause deviations from the standard DGLAF evolution equations that describe how PDFs change with energy scale. Small X dynamics have been challenging theoretically, and EIC data will be invaluable here.
Makes sense.
And as we touched on, the EIC's high precision will both necessitate and enable considering QEDFX photon PDFs, isospin violation at a completely new level of accuracy. Furthermore, detailed heavy quark production measurements will provide crucial constraints across a wide range of energy scales and charged current disk measurements.
Where the electron turns into a neutrino.
Effectively, yes, by exchanging a W boson. These will be vital for separating out the contributions of different quark flavors.
It really does sound like the EIC is going to usher in a new era of precision for understanding these fundamental building blocks. And the plan is to combine all this new EIC data with existing data in global PDF fits.
That's absolutely the long-term goal. The main future direction is to use the rich, precise EIC data along with other relevant hadronic data to explore and understand the deep connections between these 1D collinear PDFs and the more complex multidimensional TMDs and GPDs that describe transverse momentum and spatial distributions.
Bringing it all together.
Eventually, yes. Expanding current collinear PDF global fits to include simultaneous analyses of these more intricate distributions. Several leading TCD analysis groups have already done impact studies using simulated EIC data, pseudodata, to assess potential improvements.
And what do those studies show?
They consistently show the EIC data has potential for really significant reductions in PDF uncertainties across different X regions and quark flavors of valence, the D ratio, strange suppression, the gluon PDF. The EIC's unique ability for precise charged current dis at large X and Q is key here.
The sources even included some specific examples showing potential impact on upvalence and gluon PDF uncertainties. Looked like a really substantial reduction in error bars.
Indeed. For example, potential reductions in upvalence uncertainty by up to a factor of 5 at very high X, and significant improvements in the D ratio in an important intermediate X range. While the relative reduction in gluon PDF uncertainty at low to intermediate X might look modest in some plots, the implications for Higgs cross-section precision are still very significant. These improvements hinge on the EIC providing clean, precise data in kinematic regions poorly constrained now.
Okay, moving on to spin. We know the proton has spin 12, but the spins of the quarks inside only account for a fraction of this proton spin crisis, as it's sometimes called. It's been a long-standing puzzle, right? How will the EIC help unravel this?
A very precise determination of the spin-dependent PDFs is absolutely essential for understanding the proton's complex spin structure, how its total spin is built from quark and gluon helicity, intrinsic spin, plus their orbital angular momentum.
The movement inside the proton.
Right. Detailed knowledge of these spin PDFs at small x, and particularly the polarized gluon PDF, near delta G, is vital for accurately reconstructing the overall spin sum rules and finally solving this puzzle. The EIC is uniquely positioned to play a crucial role with high-precision data from spin-dependent dust.
So that very small X region is also key for the gluon's contribution to spin, which has been particularly tricky to measure.
That's absolutely right. Impact studies for polarized disks at the EIC strongly suggest the new data will provide valuable, much-needed constraints on these spin-dependent PDFs, including the elusive DIS.
But it might not be the whole story.
Well, the sources wisely point out that the precise impact can sometimes depend on theoretical assumptions in the analysis. To get a truly complete picture, it's likely additional channels will be needed, like polarized parity-violating disks, which gives a better handle on the overall polarized quarks distribution, and studying open charm production, which is particularly sensitive to big. The projected data on the longitudinal double spin asymmetry, APLL, looks very promising for improving our knowledge of the spin structure function, CO, and reducing uncertainties on truncated moments of gluon and quark helicity distributions.
It really is a complex puzzle, but it sounds like the EIC will provide crucial new pieces to help finally understand where the proton gets its spin. Now let's consider atomic nuclei. We often think of them as just collections of protons and neutrons, but things get much more complicated at the quark and gluon level inside nuclei. How will the EIC help understand the partonic structure of nuclei?
It's a great point. Although the LHC primarily collides protons, interpreting those high-energy collisions often indirectly relies on information from scattering experiments involving nuclei.
How so?
Well, the parton distribution functions used to model protons inside nuclei in LHC simulations are often constrained using data from electron nucleus scattering experiments. However, the theoretical treatment of DIS from nuclei introduces extra complexities and ambiguities not present for free protons.
Because the nuclear environment itself affects the quarks and gluons.
Exactly. The nuclear environment can modify the behavior of quarks and gluons within the constituent protons and neutrons. While the EIC will certainly help dissect these nuclear medium effects on the various tomographic distributions, it will also, for the first time, allow us to directly measure the hadronic structure of a wide range of nuclei with high precision, using electroweak probes and other dedicated processes. This minimizes reliance on inferring nuclear structure indirectly from free proton data.
So instead of just trying to understand nuclei by looking at individual protons, we get a cleaner, more direct look at the quark and gluon constituents within the nuclei themselves.
Precisely. Understanding the partonic structure of nuclei has been a significant, long-standing challenge. The EIC, working with data from the high-luminosity LHC upgrades, should make significant progress. The EIC provides a wealth of new, high-precision data, opening exciting possibilities for refining our models of nuclear parton distribution functions, or NPDFs.
NPDFs, okay.
Over the years, the relationship between global analyses of free nucleon PDFs and nuclear PDFs has become increasingly intertwined. Improved understanding of nuclear effects in NPDF analyses will, in turn, benefit our understanding of fundamental proton PDFs and ultimately improve prediction precision for experiments like HL-LHC involving heavy ion collisions.
Right.
The high-precision EIC data could also lead to more flexible NPDF analyses, maybe with parametrizations depending not just on mass number A, but also atomic number Z, allowing studies of a wider range of nuclei, perhaps even radioactive ones far from stability. The EIC's unique ability to use electroweak currents and study dedicated processes will be crucial for these next-gen NPDF global QCD analyses.
And these improved NPDFs aren't just important for understanding nuclei themselves, right? They impact other areas, like neutrino physics and astrophysics.
Absolutely. The expected reduction in NPDF uncertainties from EIC data has really important phenomenological implications for various neutrino measurements, particularly for ultra-high energy neutrino experiments being planned and built Grand POEMA PUEO.
Detecting cosmic neutrinos.
Exactly. They aim to detect extremely high-energy neutrinos from astrophysical sources, which often interact with nuclei in the Earth, or detectors. The probability and nature of these interactions depend critically on our knowledge of the nuclear partonic structure.
So NPDF uncertainties are a big deal there.
Often the dominant source of uncertainty in theoretical predictions for how these ultra-high-energy neutrinos interact. Impact studies using simulated EIC data on nuclear targets like gold show a really significant expected reduction in NPDF uncertainties for various quark and gluon flavors, especially at very small and very large X.
And that helps the neutrino experiments.
Directly. It translates to more precise predictions for neutrino nucleus disk cross-sections and even the probability that muon neutrinos pass through the Earth without interacting. In some cases, the reduced uncertainty from including EIC data actually removes previous discrepancies between theoretical predictions based on proton versus nuclear data.
It's amazing how the EIC's detailed look at nuclear structure can have such far-reaching consequences for other particles and even cosmic phenomena. Let's shift gears now to transverse momentum-dependent distributions, or TMDs. These seem to offer a more multidimensional view inside hadrons, beyond just the momentum fraction.
That's a perfect way to put it. TMDs take us beyond the 1D picture from collinear PDFs by also including information about the transverse momentum perpendicular to the hadron's direction of motion of the partons inside.
Sideways motion.
Sort of, yes. This gives a much richer, more complete, multidimensional understanding of the internal structure and dynamics. There are various leading twist TMDs, each sensitive to different correlations between parton spin, nucleon spin, and parton transverse momentum. Examples include R, related to the unpolarized PDF, GNL and GAE for polarized quarks in a polarized nucleon, the transversity distribution, and particularly interesting ones like FACDU, the Sivers function, describing a correlation between the nucleon's transverse spin and the transverse momentum of unpolarized quarks inside.
So TMDs let us see not just how fast partons move along the proton's direction, but also how they might be jiggling around or have sideways momentum.
Precisely. And to really understand TMDs, we need a theoretical framework, including TMD evolution, how they change with energy scale and TMD factorization, separating the short-distance interaction from the long-distance hadron structure. This involves dealing with soft gluon resonation and non-perturbative functions, capturing intrinsic hadron dynamics.
And our knowledge here is limited.
Currently, yes, especially for gluon TMDs compared to quark TMDs. While parts of gluon TMDs can be calculated perturbatively, we still don't understand much about the intrinsic non-perturbative components, like the Hoji-EROD, related to the Bohr-Mulder's effect for gluons. Recent theoretical efforts model gluon TMDs using spectator models and small x insights, but ultimately, high-precision experimental data is crucial to pin them down.
And how will the EIC help get a better handle on these elusive TMDs, especially gluon ones?
Semi-inclusive deep inelastic scattering, CDIS, is a key process for accessing quark TMDs. In CDIS, we detect the scattered electron and one or more hadrons, like pions or kaons, in the final state.
Looking at more particles coming out.
Right. By studying correlations in the azimuthal distribution, the angle around the virtual photon's direction of the produced hadron, we gain sensitivity to specific TMDs. For example, the AUT asymmetry, transverse spin asymmetry, unpolarized target, is sensitive to the Sivers function. All longitudinal double spin is sensitive to GO, and AL, longitudinal target spin, to AO.
Different asymmetries probe different TMDs.
Exactly. The EIC is expected to provide data with much higher precision for these CDIS asymmetries compared to now, allowing much more precise TMD extractions and a deeper understanding of quark structure.
And it's not just single hadrons in CIDIS, right? Dihadron production also plays a role.
Yes, that's right. Dihadron CDIS detecting two hadrons is particularly important for accessing the transversity TMD through the Collins fragmentation function.
Collins function.
It describes how a transversely polarized quark fragments into a hadron with a certain transverse momentum. Studying the azimuthal correlation between the two produced hadrons lets us extract information about the quark transversity distribution inside the nucleon.
Okay.
The EIC is projected to significantly reduce uncertainties on transversity PDFs and related tensor charges for up and down quarks, potentially reaching precision comparable to current lattice QCD calculations. Polarized T data at EIC will be especially valuable for disentangling down quark transversity from the often dominant up quark contribution.
And these tensor charges matter beyond just nucleon structure.
Yes, they have implications for BSM searches, as some theories predict contributions to processes dependent on these fundamental quantities. The sources also clarify the current factorization definition of TMD fragmentation functions, now widely adopted for more consistent global analyses combining data from different processes like EU annihilation and CDIS.
It really sounds like the EIC will open up a completely new window into the dynamic, multidimensional world inside protons and neutrons through these detailed TMD measurements. Now let's move on to generalized parton distributions, or GPDs. These seem to take our understanding even deeper, somehow connecting PDFs with elastic form factors.
That's a very accurate way to think about them. GPDs provide a rigorous framework to study the full 3D structure of nucleons. They unify the 1D collinear PDFs, longitudinal momentum, and elastic form factors, spatial distribution of charge magnetization.
Unifying momentum and space.
Essentially, yes. This connection allows us to create tomographic 3D images, revealing how partons with a specific momentum fraction are distributed in the plane transverse to the nucleon's motion. Even more fascinating, GPDs have a unique, direct connection to the QCD energy-momentum tensor.
Wow, what does that let us probe?
Really fundamental properties.
Right.
The total angular momentum carried by quarks and gluons, crucial for the spin puzzle, and even mechanical properties like the pressure distribution inside the nucleon.
Pressure inside a proton. Incredible.
Exactly. The primary experimental ways we probe GPDs are deeply virtual Compton scattering, DVCS, where an electron scatters off a proton, emitting a real photon, and deeply virtual meson production, DVMP, producing a specific meson like a pion or rho.
Yep.
However, extracting GPDs from experimental data is challenging because they're embedded within complex mathematical integrals. Physicists use various approaches: local fits to data in specific kinematic regions, building theoretical GPD models and fitting them, and global fits incorporating data from many processes.
Pros and cons to each method.
Local fits are less reliant on specific theoretical assumptions, but have limited predictive power. More sophisticated methods combine local fits with kinematic corrections or perform global parametric fits using specific functional forms. Importantly, multi-channel analyses combining DVCS, DVMP, and time-like Compton scattering PCS data are crucial for testing GPD universality, consistency across processes, and addressing ambiguities, particularly in DVCS extraction.
The sources showed a fascinating example: the transverse spatial distribution of up quarks inside an unpolarized proton versus their longitudinal momentum fraction derived from GPDs. It really gives a tangible sense of the spatial extent.
It really does help visualize something incredibly abstract. And GPDs also allow access to the energy-momentum tensor form factors, encoding fundamental properties like mass and spin. Poincare symmetry constrains some form factors like A0 total momentum and J0 total angular momentum.
But not all of them.
Right. Another form factor, the D term, D0, thought to relate to pressure and shear forces, isn't constrained by symmetry and must be determined experimentally or via non-perturbative theory. Interestingly, melon moments of GPDs, certain weighted integrals over momentum fraction x, are directly related to these EMT form factors, providing a crucial pathway.
And lattice QCD helps here too.
Yes, lattice QCD provides valuable insights into GPD melon moments via the operator product expansion and generalized form factors. There's also exciting recent progress exploring the X-dependence of GPD structure using quasi-GPDs and lattice calculations. Comparing these cutting-edge lattice results with phenomenological extractions from EIC data will be absolutely crucial for validating our understanding and could even hint at BSM physics.
It's incredible how GPDs weave together momentum structure, spatial distribution, and even internal mechanical properties. Now, let's turn to jets, these collimated sprays of hadrons produced when quarks and gluons are scattered. How will the EIC contribute to jet physics?
Jets are incredibly important because there are primary experimental proxies for the fundamental partons quarks and gluons in the initial collision. At the EIC, we'll study inclusive jet production in detail in EP and EA collisions. The sources show how this can be broken down into contributions from different partonic processes, quark-lepton, gluon-lepton, even photon-initiated processes, versus the jet's pseudo-rapidity angle.
Okay.
The projected longitudinal double spin asymmetry, ALL, for inclusive jets at the EIC looks very promising for providing crucial information on proton spin structure, particularly the gluon contribution.
And how we define or reconstruct these jets matters too, right? Sources mention different reference frames, like the lab frame and the bright frame.
Exactly. Jets can be reconstructed in the standard lab frame, like at the LHC. However, for certain studies, especially probing TMDs, reconstructing jets in the bright frame is essential.
Why the bright frame?
In this frame, the virtual photon has no momentum component along the proton's direction, simplifying kinematics. Bright frame jet measurements can be very analogous to CITES with single hadrons. Instead of a TMD fragmentation function, quark to hadron, we have a TMD jet function, quark-gluon to jet.
Ah, a jet function.
These TMD jet functions can often be calculated perturbatively, making the process particularly sensitive to the underlying TMD PDFs. Another interesting observable is the decorrelation between the outgoing lepton and the produced jet in the lab frame. This is also sensitive to quark TMD PDFs, specifically the Sivers function if the proton is transversely polarized. EIC projections for the corresponding asymmetry, AUT, look very encouraging.
In jet charge, estimating the initiating quark's electric charge gives flavor information important for spin asymmetries.
Absolutely. Jet charge is a valuable tool for flavor sensitivity, crucial for spin asymmetry measurements where different quark flavors can contribute with opposite signs. Studies involving two jets, dijets, in the bright frame might even provide a way to access gluon TMDs, which are notoriously hard to measure.
So many possibilities with jets.
And beyond inclusive jets, the EIC enables studying processes with jets and individual hadrons produced within jets. These are sensitive to both TMD PDFs and fragmentation functions, allowing separate and combined study. For instance, asymmetries related to the Bohr-Mulders TMD and Collins TMD FS can be probed by looking at small transverse momentum imbalances, or hadron momentum relative to the jet axis. Hadrons in jets are also powerful for investigating quark polarizing fragmentation functions.
It's amazing how many ways jets can probe fundamental structure and dynamics at the EIC. The discussion then shifted to jet angularities and groomed jet mass, even more sophisticated jet analysis tools.
Yes, jet angularities and groomed jet mass are advanced tools studying detailed QCD dynamics and the transition from perturbative scattering to non-perturbative hadron formation within a jet. Angularities are sensitive to energy distribution within the jet cone shape. Grooming uses algorithms to remove softer, wide-angle radiation, aiming to reveal the hard substructure more related to the initial parton. EIC studies will allow precise theoretical predictions for these in the clean EPA environment and investigate how cold nuclear matter might modify jet properties. These measurements can also help bridge the gap between ion collisions and the much more complex phenomena in heavy ion collisions, like parton energy loss in Quark-Gluon plasma.
And comparing jet production and proton versus nucleus collisions directly probes how the nuclear medium modifies jets.
Exactly. Studying nuclear modification of jets, how their rate and properties change in nuclei versus protons, gives valuable insights into quark-gluon interactions with cold nuclear matter. Sources presented NLO QCD predictions for dijet photoproduction and EA scattering, showing how the cross-section ratio, nucleus-proton, can be sensitive to nuclear gluon densities.
And there's a formal framework for this.
Yes, semi-inclusive jet functions, SIJFs. By looking at ratios of nuclear modifications for jets with different radii, we might largely cancel initial state NPDF effects and isolate final state interactions and modification of parton showers with heavy quarks traversing the nucleus. EIC can also study jet charge modification in EA collisions sensitive to isospin effects, UVSD quarks, and their nuclear PDFs.
Finally, on jets, the sources introduced this really interesting machine learning technique, omnifold. What is it, and why is it important for the EIC?
Omnifold is a relatively new, innovative machine learning technique for unbinned unfolding of high-dimensional data. Detectors aren't perfect. They have limited resolution, efficiency, backgrounds. Unfolding corrects for these effects to get back to the true underlying physics.
The correction process.
Right. Traditional methods often use histograms, which lose information with many variables. Omnifold uses an iterative reweighting procedure with deep learning algorithms to produce weighted, simulated particle-level Monte Carlo events representing the true underlying distribution without predefined bins.
A game changer for EIC.
Potentially, yes. It means extracting maximum information from complex EIC final states, especially for multidimensional observables like TMDs and GPDs where correlations matter. Since unfolded data is stored as weighted events, not histograms, we can choose any binning or observable after unfolding, simplifying comparisons with theory and other experiments.
But it changes how data is handled.
It does present interesting challenges for data storage, analysis tools, and even how experimental results are published.
It certainly sounds like Omnifold will be crucial for making the most of the incredibly rich EIC data, letting us delve into QCD intricacies like never before. Let's turn now to heavy flavors, charm, and bottom quarks. How will the EIC contribute to understanding these heavier quarks?
Have heavy flavor production, charm, bottom at the EIC spans a wide Q range. Because their masses are significant relative to interaction energy scales, we need specialized theoretical frameworks, flavor number schemes like fixed flavor number, FFN, and variable flavor number, VFN, to account for mass effects correctly.
Different ways to handle heavy quark masses.
Exactly. High-precision EIC data on heavy quark production will be invaluable for rigorously testing the applicability and reliability of these schemes, likely leading to their refinement. Sources even compare different theories with existing ARA charm data, highlighting the need for more precise data, like EICs, to discriminate between descriptions.
So EIC data helps test the theory frameworks themselves.
Precisely. The EIC ushers in a new precision era for investigating hadron structure, extending to heavy quarks. While proton light core PDF understanding is sophisticated, extending this precision to the nuclear sector understanding in PDFs, accounting for nuclear environment effects is increasingly important for interpreting high-energy nuclear collisions.
Right.
The EIC, colliding electrons with various nuclei, provides a wealth of entirely new data, potentially revolutionizing our understanding of overall nuclear structure, including heavy quark distributions within them. Heavy flavor production via neutral currents at EIC is also particularly sensitive to gluon distribution. Using simulated EIC charm data indicates significant reductions in nuclear gluon ratio uncertainties from various global NPDF fits.
And what about the strange quark? Sources mention charged current interactions involving neutrinos could provide unique sensitivity there.
Yes, charged current interactions, exchanging a W boson, effectively electron to neutrino, offer a unique way to probe the strange quark C in nucleons and nuclei via heavy flavor production and heavy flavor jets. However, interpreting this data can be complex due to potential power-suppressed corrections and target fragmentation contamination.
Needs careful theoretical work.
Absolutely. Significant advances in theory and computational tools are needed to reliably extract valuable info, like gluon and strange C PDFs, from future high-precision EIC charged current data. A key challenge is distinguishing genuine nuclear PDF effects from other cold nuclear matter, CNM effects, by strategically combining EIC data with existing HERA and LHC heavy flavor data.
It sounds like heavy flavors are valuable probes of lighter quark and gluon structure, too. And what about spin structure in the heavy flavor sector?
Absolutely. Polarized EP and EA collisions at EIC provide unique, unprecedented opportunities to explore nucleon and nuclear spin structure by studying heavy quark production. Double spin asymmetry measurements in heavy flavor production give additional independent constraints on gluon polarization, complementing polarized jet measurements.
And gluon TMDs.
Our knowledge of gluon TMDs is much less advanced than quark TMDs, and heavy flavor production at EIC is expected to be irreplaceable for probing these inside unpolarized and polarized nucleons. Processes like open charm bottom or hidden heavy quarkonia production, initiated by photon gluon fusion, offer a very direct way to access gluon TMDs. In particular, correlations between charm-hadron pairs are expected to be very interesting for constraining gluon-Sivers asymmetry and linearly polarized gluon TMDs.
The sources also discussed using heavy flavors to study hadronization, how quarks turn into hadrons, and energy matter transport within a large nucleus.
Yes, a very important application. Studying how heavy flavor hadron production rates, D-mesons, B-mesons, are modified in EA versus EP reactions gives crucial insights into hadronization and how partons lose energy and interact, propagating through cold nuclear matter. Detailed theoretical analyses need higher-order QCD corrections and CNM effects.
Comparing nucleus to proton quantifies the medium effect.
Right. Furthermore, looking at hadron pair correlations at large, Bjorken-X, and semi-inclusive hadron production at large center of mass energies and backward rapidity gives info on phenomena like leading higher twist shadowing and gluon saturation. Analyzing ratios of nuclear modifications for jets with different radii, where initial state and PDF effects largely cancel, helps isolate final state interaction effects and modification of heavy quark showers in the medium.
Sophisticated techniques.
There are also theoretical approaches like generalized DG-LAP evolution within medium parton showers, often using SE8 with Glauber gluons, being developed specifically for heavy mesentomography of cold nuclear matter at EIC. Finally, sources briefly mention quarkonium production at small transverse momentum using TMD factorization and NRQCD, relating measurements to quarkonium TMD shape functions.
And the detectors are designed for this.
Yes. Conceptual tracker designs for the proposed EIC detectors, Athena, ECCE, include sophisticated silicon and vertexing tracking layers and forward-backward silicon disk for excellent tracking coverage, up to 3.5. Simulations with the forward silicon tracker, FST, indicate expected momentum and displaced vertex resolution, crucial for cleanly identifying short-lived heavy flavor hadron decays and boosting signal-to-background ratio.
It really does sound like the EIC will be an absolute heavy flavor factory, providing unprecedented data to address a huge range of fundamental questions. Let's move to our final topic. Physics at very small Bjorkenx. This is where gluon density gets extremely high, potentially leading to interesting nonlinear QCD effects.
That's right. At very small X probing at very high energies or small momentum fractions, gluon density inside protons' nuclei gets so large they can no longer be treated as non-interacting. They start interacting, recombining, leading to gluon saturation and nonlinear QCD dynamics.
A different phase of QCD matter.
Potentially. A key experimental signature in DIS is the predicted suppression of the nuclear structure function ratio, RAX-Q-QA, compared to linear collinear factorization predictions, which ignore gluon interactions. Sources show theoretical predictions for this ratio with and without saturation effects for different nuclei, highlighting EIC's potential to observe these nonlinear phenomena.
Other probes.
Another important set are diffractive processes in DIST DVCS, diffractive vector meson production where the protonucleus remains intact, the ratio of diffractive to total DIS cross-sections, and the ratio of exclusive vector meson production cross-sections, nucleus versus proton, are predicted to behave differently in models with saturation versus linear QCD evolution.
So looking at how protons' nuclei appear to very high-energy electrons, low X, might show direct evidence of gluon saturation.
Exactly. The BFKL evolution equation describes expected gluon density evolution at very low X. Interestingly, HERA jet measurements showed deviations from standard DGLAP predictions at low X. Models incorporating CCFM evolution, aspects of both DGFP BFKL, seem to describe HERA data better. The EIC, with potentially reduced jet energy angle uncertainties, should make unique, important contributions to these low X evolution studies.
And low X matters for spin, too.
Yes, the small X region is incredibly important for understanding nucleon spin structure, particularly the gluon contribution, which remains a significant part of the spin puzzle.
And the theoretical framework for small X is still developing. Sources mention challenges.
Yes, significant recent theoretical developments aim for better understanding of semi-inclusive processes, single hadron digit production at small x, but calculations face challenges, like getting negative cross-sections in some regions physically nonsensical. Various theoretical approaches are being explored to resolve these different rapidity factorization schemes, resumation of large logarithmic terms. Despite challenges, recent comprehensive analyses using the saturation framework with higher-order QCD corrections show promising results describing existing forward hadron production data. But a complete, universally agreed-upon theoretical framework for many small x processes, especially at next to leading order, is still active research.
The sources also touched on more advanced concepts, light front wave functions, color charge correlators, even entanglement entropy, all in the small x context. Sounds like pushing the boundaries of quantum field theory.
They certainly are. Recent theoretical work using light front truncation approximations tries to determine initial conditions for small x QCD evolution by systematically including higher Fock states in the proton's wave function description. This goes beyond simpler Gaussian-like approximations for large nuclei, allowing calculation of color charge correlators related to GPDs.
Including more partons matters.
Yes. It significantly impacts predictions at very small x relevant for gluon evolution and spin-dependent TMDs like the gluon-Sievers function. The intriguing concept of entanglement entropy and the small x gluon density matrix is also being explored to address the apparent paradox of a pure quantum state, proton, behaving like an incoherent parton collection with non-zero entropy in DIS. The idea is tracing out unobserved parts of the complex hadronic wave function generates this apparent entropy via entanglement.
Mind-bending stuff, but it highlights how EIC probes not just static structure, but the fundamental nature of quantum fields and observation in high-energy interactions.
Absolutely. The EIC is poised for a truly deep dive into the most fundamental aspects of matter and the forces governing its behavior at the smallest scales.
Well, we've certainly taken our own deep dive today. Let's quickly summarize some key takeaways. The Electron-Ion Collider promises to be a truly revolutionary machine with the potential to unlock many of the deepest secrets of the strong force, providing an unprecedentedly detailed look inside protons, neutrons, and nuclei, and revealing the dynamic behavior of quarks and gluons.
What's truly fascinating is the sheer breadth and depth of its potential impact. I mean, from exploring exciting possibilities of physics beyond the standard model to making the most precise measurements ever of QCD and investigating fundamental origins of mass, spin, and nuclear binding. The EIC is really set to redefine our understanding of the subatomic world.
By joining us on this deep dive, you hopefully now have a much better appreciation for the inherent complexity and incredible richness of nuclear and particle physics, and for the truly exciting science the EIC will enable in the coming years. This machine represents a major leap forward in our quest to understand the universe's fundamental building blocks and forces, with a very real potential for new discoveries that could fundamentally reshape our understanding of matter itself.
Which all leads to a really profound question to ponder. Considering the immense potential of the EIC for unprecedented insights into the strong force in matter's inner workings, what other seemingly fundamental aspects of our universe might still hold profound, unexpected secrets, just waiting to be uncovered by future scientific endeavors?
A truly thought-provoking question. This incredible project is really a testament to human curiosity and the collaborative spirit of the global scientific community, with researchers from all corners working together to bring the EIC to life. Thank you so much for joining us on this deep dive.